Good morning. Glad you're here. Welcome. Thanks for attending class today. Today we're going to be looking at what happens if something's not growing. And we've been looking at some situations most recently where we've been talking about account balances that are earning certain interest rates. And we know that if we have compound growth of an account, that can be modeled by a geometric sequence. We've got our initial balance, which is our zeroth term, and then from there we have our common ratio, which is our multiplier. If we're earning 6% per year, the multiplier is 1.06. And we've also talked about compounding periods and how you might be compounding that 6% more often than once a year. If you were compounding the 6% every single month, your interest rate for each month would be 0.5, right? So you would be, your multiplier would be radically different, but you would have 12 compounding periods instead of just the one. So today we're going to be looking at what if it does not grow exponential decay. So to learn more about functions today, we're going to study a new situation in which exponential functions decays, which the exponential function decays or decreases. This will lead to a studying applications of negative exponents. So we've definitely looked at negative exponents, and some of us are still under the impression somehow that a negative exponent indicates that we're subtracting something, and we're not. It's still it's a positive number, right? But it's a reciprocal, so we're going to keep looking at that. The activity that we would do in class, and I think we will do it in class if you're in class today instead of a distant student, it involves this thing that it's called the Penny Lab. And essentially what happens, where is that at? Yeah. Essentially what happens is there's a box here with 100 pennies, and we're going to take all of those pennies and we're going to dump them out on the table. So just kind of randomly dump them out. There they go. And we're going to look at all of the pennies, get them so that we can see the heads or tails. And for all the pennies that are not showing Lincoln's face, we're going to take them off the table. And I'm going to record how many I'm taking away. Or actually, I'm going to record how many are left. So I do this, and let me pause the video. You don't need to watch me sorting them, but let me do this real quick. So I started with 100 pennies, and I went through and I took all the ones out that didn't have President Lincoln's face showing. And after I did that, I ended up with 42 pennies remaining. So I went from 100 to 42. So now I'm going to do it again. I'm going to take all these pennies, put them in the cup, shake them up, and throw them out. And by cup, I mean a box. Okay, same thing. I'm going to flatten these all out and remove all the ones that do not have Lincoln's face. Okay, so I just did it again, and now I only have 22 remaining with Lincoln's face. Let's do it. Let's do it again. This time only 10 pennies remained. Let's do it again. All right, that time I got 6. This trial I got 2. Let's try it again. Let's take these 2 and put them down. Oops. I got one was heads and one was tails, so it went to 1. Let's flip this again. It went to 1. Flip it again. Off camera, but it went to tails. So finally I got to 0. So what you can see here is every single time some of the pennies stay, some of the pennies go. Now, I've been collecting data like this from classes for many years, I think almost 7 years now. And when I collect it, I always make it a point to write down a data table. So I think this was my 2019 lab, so this was 2 years ago. But you can see I have the number of trials, and then so starting with 100 pennies, after the first trial, this group had 58 different pennies, trial 2, 3, 4, and then eventually, right? Eventually, they end up at 0, right? Yeah, it eventually ends to 0. I'm going to say safely, although there's a chance it will never go to 0. No, eventually it goes to 0. And then if I look at this as a graph, you can see I've also plotted these. So you can see this first dot right here is showing that the initial 100 pennies that everyone has. And then there's all these different groups, and then you can see how many different pennies that group had after the first trial, second trial, third, fourth, fifth. Well, as we look at this, we can see, okay, clearly the pennies are decaying. And in fact, the probability that a penny will stay is, any particular penny will stay, is 50%, right? 50% it's going to be heads, 50% will be tails. So we see this thing that we call decay, and it's actually exponential decay. And my multiplier for this sequence, if I was going to think about it, would be 0.5. But I can also think about this, right? My multiplier is also, I could also write my multiplier as it's 2 to the negative power, right? 2 to the negative 1. Okay, let's continue reading from our textbook. So in question 54, you would have gone through and collected that data. And then for question 55, we decided that the trial was our independent variable, right? So trial 1, trial 2, and we ended up creating a graph that looks like the graph you saw here. And so yeah, my independent variables along the x-axis, these are the number of trials, and the pennies that remain, those are pennies that still had Lincoln's face showing. Those were the ones that remained, and this is what we observed. So that was 55, create that graph. And there is a thing, does the graph in part F look like any graphs you have seen previously in this course? What are the first few values of this function? So, yeah, it does. It looks like graphs where the thing that I'm multiplying by, b in an exponential function is a fraction, right? It's a fraction between 0 and 1, and I can represent those with negative exponents. All right, question 56, half-life. So carbon-14 dating is used to approximate the age of ancient discoveries and learn more about things like dinosaur fossils. Scientists have studied the rate of decay for carbon-14 and have learned that no matter how much of this element they start with, only half of it will remain after 5,730 years, 5,730 years. So that number, 5,730, is called the half-life of carbon, because it's the amount of time that has to pass for half of the carbon-14 to go away. All living things on the planet have the same proportion of this carbon-14 relative to the amount of overall carbon in their bodies. So we all have carbon, right? We're carbon-based life forms. Some of our carbon is carbon-14, some is not. And the thinking is that currently and in the past, that proportion of carbon-14 was the same. So if that proportion was the same, then we can look at how much carbon-14 a fossil has currently, and we can then go back in time to where that proportion matched what a living organism's proportion would match, and we could say, okay, then we would say that this thing is so old. So knowing how much carbon-14 to expect, scientists can then measure how much carbon-14 is left in ancient items to figure out how much time has passed since the object was living. If a living object is supposed to contain 100 grams of carbon-14, and that's based on a couple of things, right? What's its size, and what proportion do we expect of carbon-14 to comprise that? So we're simplifying this a lot. We're just saying, suppose it's supposed to contain 100 grams of carbon-14. How much could be expected to remain after one half-life? So if it's supposed to have 100 grams, then that means that after one half-life, after 5,730 years, we would expect it to have 50 grams. And then after another second half-life, after two half-lives, we would expect it to have 25 grams. So you see the idea here, right? We're just showing that over time, the amount of carbon-14 left is decreasing, and in fact it's always cutting. Interesting name, half-life, where it's cutting in half. Draw a graph showing the expected amount of Y of carbon-14 in grams remaining after X half-lives. So we know if there's been no half-lives, right, we were told that we expect this organism to have 100 grams. Let me go down to this camera. So if this is 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5. So for carbon-14, each one of these half-life intervals represents 5,730 years. So, and these are grams, and at this would be 50 then in the middle. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Very crude graph. I should have some graph paper. But at times 0, right, we expect to have 100 grams in this organism. After 1 half-life, we would expect that to be 50. After 2 half-lives, we're looking for about 25, in between 20 and 30. And then at 25, 12.25 is 12.5. 12.5, 6.25, so you get the idea. So pretty quickly, what do we have here? Well, we've got pretty much exactly what we just saw with the Penny Lab. We see that over time, the amount, in fact, I didn't realize it. They said 100 grams and we had 100 pennies. So if you have 100 pennies, right, every single time the half-life goes, you expect about half of the pennies to remain. And similarly with the carbon-14, we would expect about half of that to remain. So let's continue. It says, write an equation for a function that represents the amount of carbon-14 that will remain after X half-lives. Okay, so I know that if we go down here, I know that we have an initial value of 100, so our 0th term is 100. So I could say that Y is equal to 100 times 1/2 raised to the X power. So every single time we move forward, right, we're just multiplying by 1/2. So half remains, half remains, half remains. Back up to here. Let's go to 57. In addition to helping you learn about exponential decay, half-life also provides insight into the meaning of exponents that are negative or 0. Using your function from the previous problem, what output does your function give for x is equal to 0? Okay, well, if x is equal to 0, we know that anything to the 0 power is 1. So for this function, if x was 0, if I plug 0 into there, 1/2 times, or 100 times 1/2 to the 0 power is 1/2 times 1, I would have 100 grams of carbon-14. Does that make sense? Justify why or why? Yeah, that makes sense, because we know if no time has elapsed, we have all the carbon-14 that we started with. So according to your graph, how much carbon-14 should there be when x is -1? Use this information to make sense of the value of, that is very interesting. So that's a typo. What that should say, and I don't know if I could, I don't think I could change that. Yeah, let me change that. Yeah, that's what that should look like, 1/2 to the -1. So if x is -1, right, what should happen here? So if we go back down to this thing. So if I think about this table, the way it's working, when x is 1, I was at 50. When x was 2, I was at 25. When x was 3, it's half of that, 12.5. 4 should be 6.25, etc. So as I move forward each time, right, what am I doing? I'm multiplying by 1/2. I'm multiplying by 1/2. Now, if I was to go backwards on this list, right, if I was to go the other way, every single time I go this way, I would be doubling, right? 25 times 2 would be 50. 50 times 2 is 100. 100 times 2 would be 200. So way up here, when x is -1, I would expect to see 200. So that means, if you think about it, when I have a negative exponent, when I'm looking at this expression, 1/2 to the -1 power, that has to be the number 2, right? That has to equal the number 2. Now, let's confirm that on our calculator. In fact, the book says to do that. It says confirm this with your calculator. So let me bring the calculator up. If I turn that on, I'm going to take the number 1/2, right? So I'm going to go open parentheses 1 divided by 2, and I'm going to raise that to the negative. Now I'm not hitting minus, I'm hitting -1 power. And when I do that, I get the value of 2. So when I have an exponent of -1, it's giving me the reciprocal, right? 1/2 to the -1 power turned it into 2. In fact, if I want to test that, let me see something else. I'll open parentheses, I'm going to go 1 divided by 8. If I raise that to the -1 power, my expectation is that's going to say +8. And it does. Now, if my exponent is something other than 1, it's not just the reciprocal, but it is this reciprocal and then raising it to that power. So this idea of a negative exponent, negative exponents are, they do not produce negative numbers, they produce reciprocals. So now it says, now calculate the value of your output of your function when x is -2. Well, if I just follow this pattern back, right, if I go back one, I'm totally expecting that if I hit -2, that I'm going to get the number 400 and for that function. But this is this is another typo that I'm not going to fix. Well, I can fix it. The typo is this value is supposed to be right here. This is not supposed to be that. That's supposed to be 1/2 raised to the -2nd power. I'm off screen there. 1/2 to the -2nd power. So if I think about that, if I was to square 1/2, if that was a positive power, it'd be 1/2 times 1/2, which would be 1/4. But because it's a negative power, it's not going to be 1/4. It's going to be the 1/4, but then the reciprocal. So if I take 1/2, open paren, 1 divided by 2, I apologize, 1 divided by 2, and I raise that, oops, I wanted to close the parentheses, and I raise that, get back down here. Oh, I apologize. 1 divided by 2, close paren, raised to the -2 power, right? 1/2 squared would be 1/4, and then it's going to be the reciprocal also. So I get the number. I do. Okay. So at this point, there's so many typos here. This is just heartbreaking. So let's move on. Well, and you know what? I summarize this, and actually probably in your notes you should just write that down. It says, what is the effect of a negative exponent? A negative exponent creates a reciprocal. And it doesn't mean that it necessarily turns a fraction into not a fraction, right? It's just whatever it is, even if it's a whole number and it's 5/1, that's going to become 1/5. If it's 1/5, it's going to become, in fact, if I think about that, I could have the number 5 and I could raise that. Oh, let me put the calculator back up there. You didn't see the calculator that time. If I have the number 5 and I raise that to the -1 power, right? Watch what it does. It's going to turn that into 0.2. And you're like, what's 0.2? Math, frac, right? That's a 1/5. So 5 to the -1 is 1/5. So it says, what is the effect of a negative exponent? The effect of a negative exponent is it becomes the reciprocal. And then let's grab a picture of this and look at question 85 together. So our instructions here are to use your answer from part D. And what was that? Well, we said, what is the effect of a negative exponent? And I said, it makes a reciprocal, right? So I raised it to the power, but then it's the reciprocal of it. Use your answer from part D of problem 57 to rewrite each of the following expressions in a different form. If you and your team members disagree, check your results using your calculator. So if I look at this very first one, I think, well, I could do that. Even right here, I've got this calculator. I could just go up, grab the 1/5, and I could say I want to raise the 1/5 to the -1 power. And lo and behold, look what it does. It puts it back to 5, so it gives me the reciprocal. So this is the number 5. If I have 5/8 to the -1st power, it's going to be 8/5. I know, I know, we disagree, right? You don't agree with me. So I'm going to go 5 divided by 8. And I'm going to ask the calculator, I'm going to hit math, frac, ask it to display it as a fraction. And I'm just going to take that value and raise it to the -1st power. And watch, 5/8 becomes 8/5, just like that. It's the reciprocal. How about this thing? So if I was to square 1/3, it would be 1/9. But this is not 1/9 because it's got a negative exponent. It's going to be the reciprocal. So I flip the fraction and then square. So this should be the number 9. This thing right here, 2/3. You know what? If I flip it, I could do this. This is going to be 3/2. And instead of raised to the -3rd power, it's going to be to the positive power. Interesting, huh? I feel like there might be some applications here for when I ask you to simplify expressions that are monomials. Because now it looks like we can look at negative exponents and think of them as reciprocals. They move numerators and denominators if the whole thing's raised to a negative power. So this, the numerator then 3 times 3 times 3 is 27. So this should be 27 over 8, which doesn't reduce. And I'm going to call in the referee here and look at this on my calculator. So I'm going to go 3 divided by 2. But I want that to look like a fraction, so I'm going to kick it into a fraction. And now that I have it as a fraction, I'm just going to hit raised to the -3rd power. The -3rd power. Oh, I did this wrong. The original problem was 2/3. I need 2/3. So 2 divided by 3. Whoops. Oh, my apologies. 2 divided by 3. And then I'm going to take that and make it a fraction. And then let's kick that to a -3rd power. So this thing to the -3rd power. And watch, here comes 27/8. Just like magic. Oh, and here's one with the, oh, this is cool. Look at this. This is going to be the same thing as b over a squared raised to the 1st power. And because it's raised to the 1st power, we can just leave it alone. That's just b over a squared. Reciprocals. Huh. How about this one? Okay, so I can make it a positive exponent by flipping the fraction. So it's going to become y squared z. That's going to go to the numerator. And this x is going to go in the denominator. And I'm going to cube the whole thing, right? To cube it means to multiply 3 copies of it. So I could do this also as a numerator and denominator separately. But actually this is just going to be y to the 6th power z to the 3rd power over x to the 3rd power. So y squared cubed, right? Y squared to the 3rd power is y to the 6th. Z to the 1st cubed is z cubed. X to the 1st cubed is x cubed. So this is what this expression becomes. All right, class, that's it. I hope you have a great day and that you got some good ideas about what negative exponents are and how they work. I look forward to see you in class next week. Have a great weekend.